Mhm. Oh, I see the speaker is here. Okay, so let me introduce the today's speaker, Nikolai Vovchanskii, with the talk Convergence of one-point densities for Arratia flow. Please.
Thank you. So, what I will be talking today about is a joint work with Professor Dergonts. And can we get slightly bigger now? Okay. So I will speak about one result about the convergence of specifically one-point dimensional densities for Arratia flows. So I will not talk much about the definition of the Arratia flow with drift or without drift, since it's a pretty frequent guest on this seminar. I just want to give a quick introduction for those who aren't familiar, that we have a system of linear processes that move independently before they meet, and they coalesce, merge afterwards, and move as one particle without changing its diffusion. So introduced it was by Arratia and independently, effectively by Kallis, Stott, and Werner. Effectively, the constructions that can lead to Arratia flow was discussed in Harris. Dergonts introduced it as a limit of smooth stochastic flows, and as a random element in specific functional space, it was considered by the people from the last publication. So the formal definition is as follows. So we have a system of random variables such that for every starting point, we have a semi-martingale, which is sum of Wiener process with respect to the joint filtration plus some part of bounded variation. They do not cross each other and they coalesce. The Arratia flow with drift specifically, XA, was introduced by Dergonts in 2007. So let's start with a very quick discussion of the existence of such flow, because it may require some words to be spoken. So effectively, the flow exists and is unique in terms of finite dimensional distribution. So we do not discuss it as an element of subfunctional space. At the same time, what is important when we say flow, it's somewhat a misuse of a term, since we do not speak about two-dimensional system of random mappings. We speak only of a collection of random mappings. And the proof of the theorem is effectively to use the Wiener solution. So you consider the first simplex and define your finite dimensional moments until some coalescence happens, and then you could proceed further on the corresponding edge. The object which is associated with the Arratia flow and which we are interested in this talk is the point densities. So the point density corresponds to the point measure that is generated by the flow, and the form of it is given here. It is known to be locally finite, and it can be described in terms of this k point densities that they are just defined by this very relation. So effectively, this is factorial moment, as we will see in a moment. Of course, if you take instead of f just an indicator of some set. Last time I was giving a talk on the seminar, I was discussing some results from this paper of Dergonts and Vovchanskii, 2020. And so I will not repeat discussion of results about such point densities. I will only say that it is now a full characterization of this density for the Arratia flow with zero drift in terms of preference. And it was derived independently by Maser and Ben Abraham and by Tribe and Zabronsky, but it should be said that Maser and Ben Abraham are physicists, so their paper is very physical. And alternative representation in terms of some exponential of Brownian bridges, if we consider only a finite number of starting points instead of the flow. So here we consider the whole flow, but we can consider not the flow starting from the whole line, but the flow starting from a set of fixed points. And that interpretation was given in this paper. I want to give a very quick overview of that result because it is related to the general topic of the talk. So we can decompose this density. So this is our starting point, U1, UN, into a sum where sigma corresponds to a specific sequence of heating moments inside this n-dimensional motion. So we have our points, our particles, we can give them numbers. I can look in which sequence, in which order they meet or do not meet. And this is a uniquely defines this so-called coalescence scheme. And then you can derive the description of this density in terms of just standard Gaussian densities by essentially considering the points that have survived up to the point in time t capital, the points that have died, here is the part that corresponds to the points that have died, this is the points that have survived, and this is the point that hit our J points, which are used to define a J point density. I will not speak much about this term, but let me give a very quick, I'm sorry. So this term is defined in terms of some meeting times. In some non-random randoms are defined by our coalescence scheme, and is given in terms of stochastic integrals with the Spain to Brownian bridge. So this is bridge, and one can rewrite this as an integral with respect to the Brownian bridge itself. An alternative definition of the key point density is given here. So the first equality is just a rewriting of the initial one. And the second one is actually has to be proven. And it can be done using this very representations that we just discussed. So for one point densities, we just arrive at a very similar relation, and we'll speak about one point densities, understanding this in terms of this very definition. So just delta minus one, the probability that we hit this small interval at time t, starting from 0. The general questions that we were addressing, can you prove that something like this happens in a proper sense?
Koля, may I ask a stupid question?
Yes.
In the definition, how should we understand the intersection of the image of X and the Cartesian product of sets? So I mean, formally, X it is a subset of R, and Cartesian product it is a subset of RK.
Oh yes. I think I wrote something wrong here. This means that we hit. This actually stands the
just
product.
consider XA RT in K power.
Yeah. Yeah, or just place here K G K.
So it could be that every interval can have more than 1 point from the
Yeah,
Arratia
yeah.
flow.
This
Yes.
stands the number of points that hits this interval.
Okay.
So this is a proper definition.
Okay, thank you.
And then we move from this definition to just the indicator that there is at least 1 point here. So instead of considering this, we only care that at least some point hits this, UG plus delta. So returning to the main problem, can we prove the convergence of k-point densities in general if we have some sort of convergence happening for the initial drifts? One can say that a viable approach would be to use this theorem, because you will need only to prove that this term converges in a proper sense. And that can be decomposed into the problem of conversion of stochastic integrals, plus some technical details. The downside of this approach is that it's not directly clear how to obtain estimates of the speed of the convergence. So today I will be discussing another method of proving this.
Koля, still, I'm sorry, but one more stupid question. You said that when we compute the k-point density, we calculate a number of points. But after the definition, no, please go down. After the definition, you define the 1-point density as a probability that the set is non-empty. It means that you just care whether there are points or are not points, but
Yes,
you don't take into account how many points are in the interval. So then how does that correspond, or is, I mean, to the fact that you said before that we care about how many points are in the interval?
Maybe I was misspoken, because we do not care. This is the point of this slide. So we can,
okay, we just see whether there are points or are not points. Okay.
Yeah, and this happens because delta goes to 0. So in the end, there is small probability that there are 2 or more points.
Okay.
And this is exactly how it is proven. So this probability tends to 0 as delta goes to 0 in a good fashion, so it doesn't influence the limit.
Thank you.
You're welcome. So the main result which I will be discussing today is as follows. We just have 2 possible conditions for the initial drifts, and then we have the convergence of the initial 1-point densities. I will speak about the case of k-dimensional densities in the end. So let me speak quickly about the dual flow. There is a formal definition of what a dual flow is, but right now I only care about this picture, that if we have our Arratia flow, we can define a flow that lives in opposite direction with respect to time. So this is our initial flow, moving from 0 to t. The dual flow lives is a flow that is backward in time, and the trajectories of the dual flow do not intersect the trajectories of the initial flow. This allows to speak about the probability that we have at least 1 point at this in this interval at time t in terms of the dual flow allowing displaying such behavior that trajectories of the dual flow particles within the dual flow that start from UG and UJ plus delta do not meet on the interval from t to 0. And we are interested in the result established by Ryabov that the dual flow of the Arratia flow with drift A is just the Arratia flow with drift minus A. It is stated slightly different in the paper, but it allows an extensions. So the idea is to move from the point densities to the corresponding Cauchy problems for parabolic equations. So let's speak about unique weak solutions to this system of stochastic differential equations, where W1 and W2 are independent standard Wiener process. So this is not particles from the flow, they do not coalesce, do not merge. Then we describe the first moment they meet. And using the definition of the dual flow and the picture I've drawn on the previous slide, we can establish this result. So instead of speaking about limits of the number of points in terms of number of points that hit this interval, u plus delta, we can just go for the system of stochastic differential equations as the heating time for them. By dw, I will always denote through the whole talk this object. So of course, we have no drift. It can be this density can be calculated directly. In case of the linear drift, it's also possible because one can solve the corresponding stochastic differential equations for a difference for position of difference of two particles and obtain this expression. And of course, it holds that we have our convergence. So the idea is very standard right now in the sense that we consider instead of directly probabilistic formula in terms of heating times, the solution, however, a distribution solution to the standard Wiener, to the standard Cauchy problem. So we have our Laplace plus the sum that corresponds to the newly defined operator. And we expect, of course, this to happen. Or this, or any, or a good combination of these two terms. There is a problem here that if you want to do everything extremely precise, we need to pay attention to D2 being unbounded. It means in general that this problem has an infinite number of solutions. But as usually one expects that there is only one bounded solution, and this is a solution that admits probabilistic interpretation. And the second idea that goes along with the previous one is that we then can apply a very standard Duhamel principle. If you consider this second term here as a source term, Duhamel principle tells us that this integral relations should hold, where G is the density of the two-dimensional standard Wiener process killed upon leaving first simplex D2. Taking this as an initial starting point, we can proceed iteratively and define the solution as the series of this form. So this is, of course, just the probability that the process with no drift doesn't leave the initial simplex in time t, and then we have this recurrent solution. As of now, this is a formal expression in the sense that the Duhamel principle holds for A that is smooth, but here we consider any bounded A, of course, measurable, but that goes automatically. So using this notation for differentials, where drk means k differentials and dyk means k plus 1 differentials, we can rewrite the initial representation of series in terms of this iterated integral. Again, this is just repetition. This is the form of the previous slide repeated here. The question is whether this series makes sense and how to prove that it admits the probabilistic interpretation we want. So here, results from calculus that are needed, and effectively this just means it's a series, and the derivatives with respect to special variables of the series are well defined. And this is the relations that allows us to get good estimates for the whole series and for the tail of the series for any A. It should be noticed that very similar calculations have been carried on in this paper of Drogovtsev, Zimsky, and Salki. And I'm sorry, but I do not know what is happening with this with initials just being added in front of one author. This is some bibliothèque stuff. I don't understand what is happening. We know that our series converges. We know that the derivatives converge. However, we cannot speak in terms of the second derivative with respect to the special variables, nor in terms of the derivatives with respect to time. This is because if you look at the very definition of this term, this is the factors that is getting differentiated, and it doesn't allow that to happen. So the possible solution would be to go with a weak, that is variational solution in terms of Lyons and Magenis. And there is a reference where people wrote down every detail in terms of Lyons, Magenis, Lodizhinsky, and that all, and proved that this solution admits a probabilistic representation in the sense that it has been part of a mathematical folklore for years, but this is a reference. However, we have unbounded region. We do not have the derivative with respect to S, which means we cannot just apply these results directly. One reason being that we cannot proceed just with a standard Sobolev space. We need some weighted Sobolev space and so on. However, the standard solution in case A is smooth is to use the property of this operator that is hyperelliptic, which means that the solution automatically possesses good properties. So now let us quickly discuss how it goes. So we prove this lemma that in terms of distributions, we have this recurrent relation, and of course, automatically out of this we get the final expressions that we need.
And Schwarz distributions where?
In this, on this
the product.
In product, yes.
And what are and other some boundary some conditions?
No, this means that we consider only functions that are compactly supported on this domain. So that means that we consider only W that belongs to this smooth boundary. This is,
Thank you.
So effectively, to prove this, we will write the equation for WAN in terms of sub-function Fn Ry, and we don't care precise how it behaves precisely. We just need it to be uniformly bounded, and then consider it this term that is going to be used to define the derivatives with respect to time variable. We have these two terms, which I will denote by H1, H2, and they require slightly different approaches. So the first one is the difference of fundamental densities, and the second one is just an integral from S from to S plus H of one density. And of course, we need to show these two relations. So we should take care about this difference after integrating. And this just means inner product in R2. And here we just need to get rid of this integral. So we consider only V that's compactly supported on this domain D2. Then by the green formula, we have this relation. And what we need to do, we should take care about this integral. We know that it's convergent in a good sense by Zollebeck differentiation theorem. So we just need to establish that the whole integrand is uniformly integrable on this product. So support W times interval from 0 to t times D2. This requires some calculus in the sense that one can use this simple estimation and take alpha and consider this expression. I do not consider the integrals from 0 to t integrals over support of W because it can be added for further. And the only slightly tricky moment that you cannot just use this second estimate directly. You need to split this rho to the power 1 minus 3 alpha into two terms by using some delta, small delta, that would gives you this estimate. And now choosing alpha and delta, which is possible in the way that this relation holds, gives the uniform integrability we want to have. This effectively means that we are finished with H1. To work with H2, we proceed differently. So we consider this same two solutions to static ordinary differential equations. We consider the first heating time, and we rewrite this term in terms of this functional. And it's easy to see that for every S, a convergence that we want is happening. However, we need to ensure that this convergence is consistent with the pushing H to 0 simultaneously. So effectively, we have iterated algorithm. We want to prove that it is equal to the double limit. We have iterated limit. So first of all, we get rid of our derivative by applying the Gersanov theorem. This is the corresponding exponential that is used in the Gersanov theorem. Then we can easily check, because A is bounded, so this family is again uniform integrable. And since now everything is displayed in terms of the initial Wiener process, the distribution of the heating time has no items. It's a known result because in case of drift, it's not really known for general drift. There are results there by Shiryaev, by Tenerayan co-authors, but generally speaking, it's a question. And then we can just prove that this function is uniformly continuous. And returning to the initial expressions, that would mean that we can just prove that this goes to Fn Sx, and that what we need is end. So it proves this relation, and now just passing to the limit, we obtain in the space of Schwarz distributions, we can have this relation.
Kolya, I have also a question. Here you said that you consider your solution as a Schwarz distribution on the product space, but actually you consider increments. So in with respect to time and divide. So I mean, like in the definition of the standard derivative. But I thought that if you talk about the Schwarz distribution, you need to take a test function which depends on two variables, time and space variable, right? And you need to show the corresponding equality.
It all goes down to the problem that if you consider the test function that depends on t and all other variables, instead of it, you can consider f something like this. This also provides a set of test functions. So,
Okay.
so instead of considering the general function and consider only the product of functions, and then everything splits.
But didn't you prove a little bit more than your solution is just Schwarz distribution in just in the space variable?
In the space variable, maybe I don't understand it fully.
I mean that W depends on time t, and for every t, it depends to the Schwarz space.
Yes. Yes, because this would give us a distribution. This would give us this. So this belongs to the Schwarz distribution space, the space of Schwarz distributions.
Okay.
Yes. Okay, thank you. So now we are ready to formulate our result that says that for any bounded drift, we have this probabilistic representation. We know that this series is bounded from calculus, so this is what we expect. So first we start with standard assumption that we have a very smooth, just smooth drift, and we have this relation, and operator is hyperelliptic, and that effectively means that WA is also a smooth function on the product. Then we can apply the E2 formula. It repeats the standard reasoning from book of Freilin, for instance, functional integration and stochastic differential equation. I will be given a proper reference in the end to show that in case of smooth A, the probabilistic representation holds. And then we use the modification of A. So eta is just an arbitrary modifier. So we consider a sequence of smooth functions approaching our initial function. And we rewrite the probability of this type in terms of the indicator defined in terms of the process with no drift and the stochastic exponential from the Girshanov theorem. And we need to prove two things simultaneously. We know that this equals VAN XS, and we want to prove that the upper and the lower part of this relation also converge to the corresponding entities for the flow with bad, generally speaking, drift. To prove this, we just need to check that the stochastic exponential from the Girshanov theorem convergent probability, because it's easy to check out the technical details. And to do this, you consider two integrals, the stochastic one and the ordinary one, which are inside this, the exponential separately. We start with the ordinary Lebesgue integral, or Riemann one. And you use the Lebesgue dominated convergence theorem twice in a row, using the fact that we have here just for every error, this is just an integral with respect to the Gaussian density. And of course, since A n and a0 are bounded, everything is extremely well behaved. And then applying it twice in a row, the Lebesgue-dominated convergence theorem twice in a row, we arrive at the conclusion. And the very same reasoning applies to the second stochastic integral. To prove that we have the convergence of the sequence of series, we start with the uniform bound on the tails. And this is again holds because an and a0 are uniformly bounded. And using the very standard estimation that from the theory behind the Trotter-Likatos formula, we can prove that it's sufficient to consider for fixed m and for fixed k just the convergence of this integral. And again, results from calculus allow us to do this. You need to proceed from the left side and from the right side and use some analysis in the end. This means that we have our representation of the initial one-dimensional density in terms of the series. So instead of speaking about the convergence of densities, we can speak about the convergence of the derivatives of the series. And this is how the main result is proved, but the reason used has just been discussed. So we will not talk about this. This is some calculus plus analysis. Let us speak about the initial aim and whether we have achieved it or not. The answer is, strictly speaking, negative, because we do not know the speed of convergence. Of course, one can say that due to the definition of WAN as an iterated integral, one can speak that since this is a Gaussian density, the combination of Gaussian density, one expect that only the behavior of A near the point where this is small matters. But still, we weren't able to recover the speed. Moreover, if we move to the k point density, you need to consider a slightly different situation. So even in case when you're speaking about 2-point densities, you would have u1 plus delta, u2 plus delta. You're going, and if you use the same method, you're going to speak about the behavior of the dual process for 4 points that start from the points the u1 plus delta, u2 plus delta. However, there are many situations. These two middle points may meet or may not meet. And this leads to some algebraic structure, which effectively corresponds to the Pfaffians. And effectively, this means that we are back at the beginning in the sense that we use the same system of parabolic initial boundary problems in spaces of varying dimensions that people establishing the initial representation that Pfaffians used. However, if we want to represent our solution as a series, it doesn't work, because right now the integral that should be discussed when we speak about the events, the first derivative with respect to the special variable doesn't exist. So we cannot apply this scheme as a Duhamel principle, which effectively brings us also to the representation via Brown and Bridges, because this seems to work. And to conclude, one can say that as a future work, one may need to go back to the representation in terms of Brown and Bridges instead establish the appropriate result for the convergence there. I also included the list of sources in case, so if anyone is interested, it would be possible to pause the video. Thank you for your attention. That's all I wanted to tell today.
Okay, thank you very much. And maybe somebody have questions or comments, please.
I'm sorry, I cannot hear anyone.
Excuse me, can you hear me?
Actually.
Now, Nikolai, can you hear me?
Now I can hear, sorry.
Okay, okay. So I hope everybody hear me. So please, maybe somebody have questions or comments.
I have maybe very naive question. It is regarding the convergence of k-dimensional distributions. Just about the following approach, whether you thought in that direction, or maybe it is really very naive. I mean, when you apply the Gersonov theorem to the Arratia flow with drift, I mean, or Arratia flow with drift, it appears just by the Gersonov transform from the usual Arratia flow. So therefore, now when you want to change drift or make drift dependent on A, cannot you go directly via the Gersonov transformer and, for instance, show that the exponentials, that exponents in Gersonov transforms converges when an converges to A. And then probably this you could get directly the convergence of k points densities, or it is very naive.
I think you are true. And one way to think about this is to return even to this representation in terms of stochastic exponential with respect to Brownian bridges, because it is derived from the Gersonov theorem for Arratia flows derived by Drogotsov, and this is uses Gersonov transform. And as you see here, you just need to prove that this stochastic integral, this deterministic power ordinary integral converge, and this is doable.
So therefore, when you want to talk about the convergence of integrals anyway, you must consider the partial differential equations, which corresponds to the semigroups generated by the process.
You can, because if you speak about the Pfaffen representation, what is behind it is a sequence of stochastic parabolic problems. So you consider some number of points until they meet, and that means that you have some boundary condition of the corresponding edge of your first simplex.
Look, my question is, I don't want to work with partial differential equations. Very often you can overcome the partial differential equations just going to the convergence almost surely and so on. I mean, when you can show that, then you have weak convergence, and therefore you have also the convergence in the sense of distributions, and therefore instead of talking about the weak convergence, you can talk about strong convergences. Probably you can put this into the model and have the kind of convergence without talking of partial differential equations.
Well, I think you're also true, because you can consider this theorem, right? And effectively, you just need to prove that these terms are convergent. And this can be achieved by using strong convergence. The only problem is that you, generally speaking, do not know how to define Arratia flows on the same probabilistic space.
Okay.
But if you go here, there is not going to be any Arratia flows. There are going to be only one endpoint dimensional motions, and then can be simultaneously defined on the same probabilistic space. So everything should be applicable, and everything should be exactly as you told.
Okay, thank you.
Thank you.
Thank you. Maybe other questions or comments, please.
I have one last remark that the problem with representations that I am having is that I cannot derive estimates on the speed.
Yes, this is must be noted when you answer to Vitaly, because it looks nice, but always when we have something nice, it requires some difficult job. So here we face some technical problems, Vitaly, in order to do this directly via Gersonov transformation.
Yeah. I think you can do this directly, but you can easily obtain estimates. That's it.
Yes, exactly. So let me also do some comment, and can you just go to the last slide where, maybe somewhere where I just can draw a picture, very small, but
well,
just somewhere where
maybe
it can
here.
be. Oh, okay, it's good. Because there are, of course, some technical problems, and it will be very good to have estimation of speed of convergence and the same result for n-dimensional densities. But also, it will be interesting to understand what happened when we have such kind of the drift like this one. For example, can we suppose that the mass will be concentrated when, for example, here we have just positive drift, and here we have negative, and some drift like this one. And when this attitude will go to plus infinity, we can suppose that all mass must be concentrated in the point zero or near it. So it will be interesting to understand the behavior of the related measure or point density when something approach delta function or some other generalized function. So I think that for the future work we have a lot of questions here.
I have a comment here. I do remember this question, and I want to say that when you look at the representation of this density, right?
Mm-hmm.
Then here happens very similar situation. It also, this integral is kind of concentrated. The main value of this is concentrated around this the line where this difference is getting smaller and smaller around the corresponding line. So the main problem, the main technical problem for me is that I cannot derive better estimates than this very naive estimate here, or something similar to that. So
yeah,
I thought maybe your question can be addressed if you apply something like the Trotter formula here.
Oh, why not? But it will be interesting to understand such kind of phenomena. So, as I said, we have a lot of interesting questions in this direction here. Okay, if there are no other questions or comments, then thank you very much for interesting talk.
Thank you.
And now we finish our work for this semester. And I have to note two things. Firstly, we have a new year very close, so I wish a happy new year to every participant of our seminar. And secondly, I just want to recall that the proposition for the talks for the next semester can be sent directly to Georgy Ryabov up to the end of January. We will start our seminar in the February. Now, thanks a lot, everybody, and Happy New Year. Bye.